Welcome to the next lecture in electric circuit analysis. In this lecture, we are going to discuss the introduction to Laplace transform and solve some problems. So, the introduction goes like this. We have been discussing the RLC network, either the first order or second order. So, when we have RL network or RC network, it is the first order circuit. When we have RLC network, then it is a second order circuit. So both for first order circuit or second order circuit, the governing equations are written in the form of differential equations, which are in the time domain. Now, the same problem can be solved in the frequency domain using the concept of phasors, which we have studied. Now, in this chapter, we are going to introduce a new topic, which is the Laplace transform, which will convert the differential equation into algebraic equation. So the phasors also do the same thing with the magnitude and angle, converting the differential equation into algebraic equation. Now the conversion process is like this. We can convert the time domain to frequency domain using the concept of Laplace transform, and the vice versa, the frequency domain can be converted to time domain using the concept of inverse Laplace transform. Now, what are the advantages of Laplace transform over the phasors? Because both are doing the same thing. In phasors also, we are converting the time domain into frequency domain. In Laplace transform also, we are converting the time domain signal into frequency domain. So, what are the advantages of Laplace transform over the phasors? Laplace transform can be applied to a wider variety of inputs than phasor analysis. We have seen that in the case of phasors, it is generally for the sinusoidal signal, but in Laplace transform, the input can be of various form or shape. It provides an easy way to solve the circuit problem involving initial conditions, since it works with algebraic equation instead of differential equation. So the differential equation is converted to algebraic equation, which makes the problem to be easier, and hence we can make use of the initial conditions and solve the circuit in a less complicated way. It is capable of providing one single operation the total response of the circuit comprising both the natural and forced response. We have seen in transient analysis that the response of a system is obtained as the sum of the transient and the steady state, or otherwise the natural response and the forced response. So the Laplace transform is capable of solving the entire problem in one step. Now through this flowchart, let us try to understand what is the advantage of Laplace transform. So when we have any RLC network which is to be solved in the time domain, then the system is given an input which is given by u of t, and the output is obtained as y of t. So the system is basically described by the first order differential equation, which, or the second order differential equation, or otherwise known as ordinary differential equation, which is difficult to solve because it involves the integral differential equation. Now if we go in the frequency domain with the help of a Laplace domain or transformation, then the input signal y of t is converted to u of s, that is s known as the Laplace variable, whereas the output, which is obtained as y of s, is transformed into inverse Laplace transform with the help of y of t. Now here the solution is much easier because it is to be solved using the algebraic equation, and the system is described using the transfer function, which is output by input. So Laplace transform solve the complicated differential equation problem in the frequency domain using the algebraic equation. Let us define the Laplace transform in mathematical form. So Laplace transform is an integral transformation of f of t. Given a signal f of t, its integral transformation from the time domain into the complex frequency domain, giving f of s. So if we have any signal which is in the time domain f of t, then that signal can be converted to the frequency domain f of s or the Laplace domain, and this transformation is known as Laplace transformation. The frequency domain is the complex domain. Complex domain means we have the real part as well as the imaginary part. So sigma is the real part and omega is the imaginary part. J is known as the iota or the complex variable. Now the mathematical definition of the Laplace transform, given a signal f of t, here the italic L indicates the Laplace transform, which will give us f of s. Now the integration of f of t multiplied with e to the power minus st dt, integrating from 0 minus to infinity, and this s is the complex variable, so we have the complex frequency domain. So s is the complex variable. Now if we observe the argument of s of t raised to the power e, so that has to be dimensionless. So here we have e to the power st we have, so s has to be dimensionless, as the unit of s is frequency or second minus, because the argument of s of t has to be dimensionless. Hence the Laplace variable s has the unit of frequency or second minus. Second point is the lower limit is given as 0 minus. This is to include the origin and capture any discontinuity in the signal of f of t at time t equal to 0. So where the switching has taken place at time t equal to 0, if there is any discontinuity, that also will be captured if the lower limit is given as 0 minus. Now this integral is from 0 minus to infinity, which is a definite integral, and the result hence will be independent of time because it is integrated over the time. Then only one variable will be involved in the output f of s, that is a function of the Laplace variable s. Now there are two different type of Laplace transform can be there depending upon the integration. One is known as one-sided Laplace transform or unilateral Laplace transform. So if we ignore for all signal t less than 0, means it is a step input f of t into u of t for t greater than equal to 0, then it is known as unilateral Laplace transform. On the other hand, if you have a two-sided, which is known as the bilateral Laplace transform, then you have f of s, which is the Laplace transform we have minus infinity to infinity. So entire time domain we are integrating, that is known as the bilateral Laplace transform. If we are integrating over the positive time frame, that is known as one-sided or unilateral Laplace transform. In circuit analysis problem, we will concentrate only on the one-sided Laplace transform because that will be adequate for analyzing any electric circuit. A function f of t may not have the Laplace transform. So it is not like always a signal will have the Laplace transform. There may be cases when there is no Laplace transform. To have a Laplace transform of a signal f of t, the integral must converge to a finite value, because there is an integration involved which is a definite integral, and we are integrating over one-sided, that is 0 minus to some time, or otherwise we can say infinity. Then it should converge to a finite value, then only we can say that the function will have the Laplace transform. We know that some time t, the modulus of e to the power j omega t will be 1. Hence the integral will converge when the integration of the Laplace transform function will be less than infinity for some sigma, which is the real axis of the frequency domain, equal to sigma c. This we can understand in the graphical format, where the real axis is the sigma axis and the imaginary axis is the j omega axis. Then the region of convergence from where the Laplace transform will be valid is when the Laplace function modulus should be less than infinity. It means it should have a finite value. Then the sigma has to be more than sigma c, which is the convergence variable sigma, which is on the x-axis. So sigma, if it is more than sigma c, then this is the region of convergence where you will be having the signal having finite value. F of s is undefined outside the region of convergence, hence there is no meaning of the Laplace transform. Now we have converted the time domain to frequency domain using Laplace transform. So the frequency domain signal can be converted to time domain using the inverse Laplace transform. So we will have minus raised to the power of L, that indicates the Laplace transform of f of s, which will give us f of t in the time domain. So it will be equal to 1 by 2 pi j integrate from my sigma 1 minus j omega to sigma 1 plus j omega f of s e to the power st ds. Now here the integration is in the ds function. We'll solve one problem to understand the Laplace transform. So with the given function, we have to obtain the Laplace transform. So let us see what are the different functions we have. If we have the step function and we have to obtain the Laplace transform, then we are integrating and the magnitude will be 1 in case of the step function, and the definite integral from 0 minus to infinity will give us 1 by s. So Laplace transform of u of t, that is the step function, will be equal to 1 by s, and this is the function of s. So we see that Laplace transform is a function of Laplace variable s. Similarly, if we have e to the power minus at ut as the function and we want to obtain the Laplace transform, then we will obtain, after integrating, we will obtain 1 by s plus a. So if we have impulse function del of t, the Laplace transform will be 1. So here we can observe that if the signal is time shifted, we are having s plus a in the denominator. Similarly, if we have some sinusoidal signal, sine of omega t, we are integrating from 0 to infinity. In case of the Laplace transform, we will get omega by s square plus omega square after obtaining the definite integral. So we have taken few examples of the time domain signal and try to obtain the frequency domain output of using the concept of Laplace transform. Now, what are the different properties of the Laplace transform? There are different properties we will describe, like the property of linearity, scaling, time shifting, frequency shifting, time differentiation, time integration, initial and final values. These are some of the important properties. Other properties are also there which will be discussed. So if you see the linearity property, given the two signal f1 of t and f2 of t, if that are multiplied with some scalar a1 and a2 and adding up, the Laplace transform will also involve a1 and a2 constant multiplied with the individual Laplace transform, that is f1 of s and f2 of s, where f1 of s is the Laplace transform of f of t, f1 of t, and f2 of s is the Laplace transform of f2 of t. So this is the concept of linearity. On the other hand, if we have the scaling property, that is a constant a is multiplied in the function, then we will have 1 by a f to the power s by a. So all here we have the Laplace transform of f of t will give us f of s. Now the concept of time shifting, which can be time ahead or time before, we have t minus a, here time shifting is there, so you will have e to the power minus as term here. Frequency shifting, if we are shifting some frequency that is in the form of exponential e to the power minus at, then we have f of s plus a. Time differentiation, if we are differentiating the function with respect to some order, that is nth order, then there will be having different ordered term in the Laplace variable. S to the power n term will be there, s to the power n minus 1 to s to the power 0, and the function will have f of s, which is the function real function of f of t, and then some values f of 0 minus f dash means first derivative, f n minus 1 means the last derivative. Time integration, if we are integrating the signal f of t from 0 to t and obtain the Laplace transform, we'll have 1 by s f of s. Now we have the concept of initial and the final values, like some signal we want to obtain the initial value f of 0 and the final value f of infinity, then we are putting a limit function, that is s tend to infinity when it is 0 and s tend to 0 when it is infinity. So this is reverse, and then the limit function is s into f of s. So these are few important properties of the Laplace transform, and if you want to go to all other properties together, then if there are other properties also, like the properties of convolution and the properties we have discussed: initial final value, time periodicity, frequency integration, time integration, and these properties we have already discussed. So these are the total properties that will be useful when we will solve few problems where f of t will be the given to us and we have to obtain f of s. Now, in some cases, the signal is very complicated, so it is not possible to integrate and obtain the signal f of s directly from f of t. In that case, we use the Laplace transform pairs, which are already obtained, and we will use this table to solve and get the Laplace transform pairs for the any type of signal. Like for example, if we have an impulse signal, then the Laplace transform will be 1. If we have step signal, then it will be 1 by s. If we have some exponential signal e to the power minus at, we'll have 1 by s plus a. Similarly, there are different type of functions. We have sine and cosine function. We have time shifting property of the sine signal. So these table will be useful for solving the problem rather than going by the direct integration problem. Let us solve one problem to find the Laplace transform of this function f of t. So if we have one function f of t, which is the summation of impulse function, we have step function, and there is time shifting function, we have frequency shifting function. Now we will use the properties of Laplace transform and the table data that has been given to us. Now the property of additivity we'll use for f of s, which is the Laplace transform of f of t. Then we have individually we will obtain all the Laplace transformation of the given input time signal, and from the table we can put the values of the Laplace transform. Like for the impulse function we will have 1, for the step function we will have 1 by s. Then we can obtain the function f of s, which is the net Laplace transform of the given f of t function. On the other hand, let us take one more example, which is f of t is equal to t square sine 2t u of t. In this case, we will use the properties, like we already know what is the Laplace transform of sine 2t, which is equal to t 2 divided by s square plus 2 square. This is coming from the table that is provided to us. Now we will use the concept of frequency differentiation because we have t square term here. So the property of frequency differentiation we are going to use. So Laplace transform of t square sine 2t we are going to use, and here we have the power of 2, that is the second order. So we will be using d square by ds square in frequency differentiation. So using the property of Laplace transform, we will get the answer as the final value, which is 12s square minus 16 divided by s square plus 4q. So we are using both the properties as well as the tabular values. Now we'll use the graphical functions and obtain its Laplace transform. Let us see some problem. So here, given a signal which is g of t with respect to time t, this is given in the form of graph. Can we obtain the Laplace transform? So first, from the graph we have to obtain the mathematical equations. Now the signal can be broken up into different time zones, and then we can add up in terms of step signal. After obtaining the mathematical equation, we can use the concept of Laplace properties and the tabular data. We will use the time shifting property here and obtain the g of s, which is the Laplace transform of g of t. So whenever a graph is given to us, first thing we have to do is obtain the mathematical equations and then use the Laplace properties and the table to get the value of g of s. Let us take one more signal here. Now here we have only one graph obtained, but this is a periodic signal which is f of t with respect to time t. We can easily observe that the period of this signal is 2 seconds, and so we can concentrate on only one part of the signal because it is periodic. And for the one signal, we can write what is the mathematical equation of f of t, and these will be further broke up into the sum of the signals in the time domain. Then the Laplace transform that will convert the time domain to frequency domain, we will obtain the Laplace transform of each signal individually and add up and get the final result. So we have f of s, which is for only one part of the signal, and hence since the time period is given as 2, so further the f of s, which is the net Laplace transform of the entire signal, we will put the concept of time property, that is f1 of s, which is only for one signal and it is divided by 1 to 1 minus e to the power minus ts, where the t is the time period is equal to 2. So we'll get the final answer for this. So it is a two-step process. We will first use only one graph to obtain the Laplace transform, and then using the concept of time periodicity, we can use and find the net frequency domain conversion. Now, initial and final values, how do you obtain for a function using Laplace transform? So this is the signal which is given to us, h of s, in the frequency domain. We will use to find the initial and the final value. So first we'll obtain h of 0, which is the initial value problem, and we'll find the limit, which is s tend to infinity s into h of s. Now here when we are having 0, which is the initial value, we are putting here s tends to infinity. So this equation is multiplied with s and we obtain the limit. So using the mathematical concept of limit, we find that 0 is the answer for the initial value. On the other hand, when we have the infinity term, that is the final value term, then the limit will be tending to 0, s into h of s, and using the concept of mathematics, we can obtain that final value is also 0. So here both the initial value and the final value of the signal is 0. So the first part of the Laplace transform, which is the introduction, is over, and in the coming parts we will be discussing the inverse Laplace transform, convolution, and how do we apply the Laplace transform for integral differential equation. Thank you for now and see you in the next lecture.